So there are a lot of real-world formulas that deal with exponentials and logarithms. One we're going to look at is Newton's law of cooling. So following the cooling of an item based on the temperature that it starts at, the room temperature, as well as there will be a constant value in there. So what we're looking at here is the temperature of an object, so that's what we're solving for. This T with the subscript of S is the surrounding air temperature, or you could think of it as like the room temperature. And then we have time passing, so it's times passing and the temperature is changing. A is the difference between the initial temperature of the object and the surroundings. So it's going to be a difference of where that temperature started and essentially what it would be decreasing down to. And then K is a constant that we'll often have to solve for based on the circumstances. So let's look at how we would apply this and finding this formula and then using it. So we have a pot of warm soup with an internal temperature of 100 degrees Fahrenheit. So that's the idea of our initial temperature. And it was taken off the stove to cool in a 69 degree Fahrenheit room. So this would be our room temperature. You can think of that as T with the subscript of S. And then we have this information after 15 minutes, the internal temperature of the soup was 95 degrees Fahrenheit. So what we have there is essentially a coordinate of time 15 and temperature 95. Notice they don't say what the units for time is, and basically it can be based on the scenario. So by making this 15, we're now saying time is measured in minutes. So with this, we have T with the subscript of S, we have this coordinate. So in terms of what we need to fill in on our formula, we need this value A, which we can find as the difference between the initial temperature, which is 100, minus the room temperature, which is 69. So A is going to be equal to 31. So for my formula, we're looking for temperature as a function of time. We have A of 31. We have our value E. We don't know what the constant is, and T is our variable. And then we're adding with the room temperature of 69 degrees. So we pretty much have our whole formula filled out except for K. Again, just remember E is a number. So it isn't a variable that we're plugging in anything for. It's just 2.72. That's all it is. But K we need to find. So this is where the coordinate's going to come in. We're going to solve for K. So we have temperature of 95 equals 31e to the 15 times t. Sorry, 15 times k, because we're plugging in 15 for t, plus 69. And now what we're going to do is go through this in order to solve for k. So I'm going to subtract 69 from both sides, which should give us 26 equals 31e to the 15k. I'm going to divide by 31 on both sides. So it would give us 26 over 31 equals e to the 15k. And now in this form, we can change to logarithmic form. Or you can think of it as taking the natural log of both sides. But what we should end up with is the exponent, 15k, equals the natural log, so logarithm base e, of the value 26 over 31. And then all we would need to do is divide by 15. So we'll have this natural log of 26 over 31 divided by 15. And we could go ahead and get a decimal answer there. That should be about negative 0.0117. So for our function, t of t equals 31 e, and now we're going to substitute in for k the negative 0.0117 times t plus 69. And that would be our function for cooling of this pot of soup. To the nearest minute, how long will it take the soup to cool to 80 degrees Fahrenheit? So here we're being told that the temperature is 80. So what we're going to do is plug in 80 equals 31e to the negative 0.0117 t plus 69. And our solving is going to go very similarly to what we just did up above there. So I'm going to subtract 69 from both sides of the equation. Divide by 31. Change to logarithmic form, so solving for that exponent with logarithm base e, which is our natural log of that value of 11 over 31. And with that, we would divide both sides by the negative 0.0117. So t would be equal to this natural log of 11 over 31 divided by negative 0.0117. And for a decimal answer, that should be about 88.5549. So to the nearest minute, we'll round that up to 89 minutes. So about 89 minutes. All right, our last piece here, to the nearest degree, what will the temperature be after 2.5 hours? So with this, we know time, but we don't know temperature. So we're looking for temperature. And time, what we need to remember is that our units are in minutes. So where they're telling us 2.5 hours, we need to change that to minutes. So we have 60 minutes for 1 hour, 60 minutes for a second hour, and then half of an hour of 30. So our time is going to be 150. So 150 will be the same as 2.5 hours. So with that, for our function, we're solving for t, but plugging in a time of 150. So we'll have 31 e to the negative 0.0117 times 150 plus 69. And we plug that into the calculator. And let me go ahead and show you this one since we have some pieces going on. So in Desmos, we will have 31 e raised to power, I'm going to use some parentheses here, so negative 0.0117 times 150. And then I need to hit the right arrow or click down so that I'm adding 69 on the outside. So that's going to be a 74.36. So rounding to the nearest degree, that would be about 74 degrees Fahrenheit.